Hi, I'm Antonio. I'm a co-founder at Zed Industries, and there we're building Zed, a high-performance multiplayer code editor written in Rust. I want to start this talk with a claim, and my claim is that writing correct async code is hard. Rust makes it easy to create asynchronous function, but just by eyeballing a function, it's pretty hard to understand what's it gonna do. This is a little bit of a preview of what we're going to talk about. So we're going to start with a motivating example to back that claim. Then we're going to look into a seemingly orthogonal topic like property testing, and then we're going to look into how futures work in Rust. And with that knowledge, we're going to live code a deterministic executor together. And then we're going to look at some real world example in Zed of how we use this technique to verify async code. So yeah, let's start with a motivating example. So what you have here is a simple setup. We've got a couple of clients trying to connect us to a server, and we'll get into what that does in a second. So yeah, here we have client 1, client 2 connecting to that server. And then here we're using futures join. This is just a way of awaiting these two futures together. And then we want to assert that client 1 sees client 2 as its peers, and client 2 sees client 1 as its peers. So yeah, this is how connect to server works. So imagine we have a connect function that lets you connect to a certain server. And then over this connection, you can perform requests. In this case, we're trying to maintain this hash set of peers. And so we're requesting the initial set of peers from the server. And then the connection also lets you listen for new peers connecting to the server. And so here you can see I'm passing a callback to get notified whenever a new peer joins. And so I'm maintaining that hash set. The problem with this code is that it has a bug. And before telling you what the bug is, I want to give you some moments to think about it for yourself, just as a puzzle. It's pretty subtle. It's not it. That's not it. That's fine. Yeah, we're not keeping the lock around. It's just.
You return before anyone's connected.
That's not it. Okay, I'll say what the problem is. The problem is in these two lines of code. If you squint, we're performing this request, and the problem with await is that you don't really know what's going to happen inside of that request method. Like a lot of things could happen, and so one thing could be deserializing on a background thread, right? The response from the server. And while I'm deserializing that response, some peer might connect, and I might miss that peer connecting. So like that's what you said? Okay, sorry, I didn't get that. The thought is that, yeah, these two lines are inverted, like these two expressions. Like we want to listen for peers connecting first, and then we want to grab the initial state from the server. And this bug is pretty subtle. This is something that we've encountered a lot in Zed as we were building the server-side component of it. It's pretty easy to make this mistake. And the problem is that even if you have a test like this that verifies this code, the problem with this test is that it will pass most of the time. And so like on the one hand, you might have this test passing 99% of the time, but failing 1% of the time on CI. And so now you have to investigate why that test is failing on CI, because maybe that machine is under provisioned because CI machines are typically slower. And so they introduce different races than what happen locally. And also this is an actual production bug. You could have this bug in production, and you could have clients not seeing peers, and you might be puzzled as to why that's happening. So yeah, non-determinism is a nightmare in general, whether that is in production or in tests on CI. It's always, like we've found over and over, that non-determinism is bad for your code. And so I want to turn our attention to property testing, and I like to think about property testing in contrast to unit testing. So in a typical unit test, what you have is specific inputs and specific outputs. So in this case, we're testing addition commutativity, which hopefully works, but for the sake of the example. So yeah, here we're testing 1 plus 2 is equal to 2 plus 1, 3 plus 4 is equal to 4 plus 3, and so on. And so the idea with property testing is that you can pull those inputs out and just assert about some property that you care about. In this case, we want to say that for all A and B's, adding A to B should be the same as adding B to A. And you don't know exactly what those inputs will be. And so typically this is handled by a property testing framework. I'm going to mention a couple in a second. But the main idea is that what a property testing framework does is it will run a bunch of iterations, typically a lot of them. And for each iteration, it will instantiate a random number generator. And with that random number generator, it will pass those two random inputs to the test in question. One key idea about property testing and determinism in tests is that this is a random number generator, but it's seeded, meaning if I pass the same seed, I will always get the same inputs. So no matter which seed I pass, this test is always gonna fail or pass depending on whether commutativity works, which hopefully works. So yeah, there's a couple of popular property testing frameworks in Rust. PropTest is one of them, QuickCheck is one of them. And they're really useful independently of the topic of this talk, which is testing asynchronous code. So I definitely recommend checking them out if you haven't done so already. So yeah, now you might be asking yourself, okay, I kind of understand property testing. What does it mean to property test a future? What does it mean to property test asynchronous code? Yeah, like if we look at the test that we saw before, what's the property in this case, right? And so I want to take a step back and think about what the problem was that could have caused this test to fail. The problem is given by the fact that the execution order of those two calls to connect to server is kind of unspecified. You don't really know it when you're writing the test. And so you might have client 1 connecting first and client 2 connecting second, in which case the race doesn't really manifest itself, and so the test would pass. You could have the opposite, where client 2 connects first and client 1 connects second, and that the test would pass. But the problem is when like these two calls race with each other and cause that problem that we saw before that was fixed by inverting those two lines of code. And so yeah, the key idea with this is that the property that we want to assert is that unit tests pass under all valid execution orders. We want to ideally be able to scramble the order of all the valid execution order of a certain future and be able to verify that our test passes. So in order to do that, let's take a step back and look at how futures work in Rust. So if you haven't seen this already, a future in Rust is pretty simple. It's just a trait. You can implement it for anything that you want. And the idea with Rust futures is that they're poll-based. Something has to poll them, has to call this poll function. And a future can return either the fact that it's ready or if it isn't ready, that it's pending. And so when it returns pending, you can see here we're passing this context parameter. And the idea of this context parameter is that it tells the caller, it's a way to tell the caller, hey, I'm gonna tell you at a second moment to call me again whenever I'm ready to be polled again. And so I wanted to just real quick go through how one might implement a future in Rust. This is a struct they call naive timer. It's not optimized, but I think it tells a good story. So say that we want to have a timer in Rust. We want to create a timer future in Rust. And so, we create it, we want to instantiate it with some kind of deadline when the timer has to fire. And so this is how we could implement the future. So if somebody polls us and we are already past the deadline, then we want to say that we're ready, like the future has been resolved already. If we're not ready yet because we're lagging behind the deadline, we want to capture the waker from the context. And then in this case, we're spawning a thread that will sleep for however long is left until the deadline, and then we're going to call wake. But yeah, crucially, we will return right away from this function and say that we are pending, like we're not ready yet to satisfy this timer future. Typically, that's not how you interact with futures in Rust. The more common way to do it is to write an asynchronous function. So in this case, we're using that timer future to print line foo in a loop and at a certain interval, right, at a certain rate. So yeah, so you can see here we're instantiating the function and then we're calling await on it. And this under the hood creates a future like the one that we manually implemented before. It's a state machine that makes forward progress every time it's polled or anytime it's ready to be polled. So I said before that in Rust, futures are poll-based, meaning something has to poll them. And so the thing that could poll them is another future. But at some point, these futures need to be driven forward. So like something has to take care of like pushing the future forward. And so typically, this is implemented by an executor. And an example, super popular example of an executor is Tokyo. There is async standard. There is small. There's a lot of them. But yeah, the two key functions typically on these executors are block on and spawn. So block on will literally block the current thread until the future is resolved, whereas spawn will delegate to the executor the job of pushing that future forward, and so the caller doesn't really know how that future is being driven forward. But interestingly, yeah, the executor gives you back a handle. And this handle will resolve once the future is done. So you can, await that handle to check the output of the future. But the future will be, you don't need to await that future. Like the future will be moving forward automatically by the executor. And so I thought it would be interesting to see how one might go about implementing block on if you were to create an executor. So here you can see we're creating that print foo future, like we're calling print foo to create that future. So we want to print foo at an interval of 1 second. And so yeah, we're pinning the future. We're not going to get into pinning in this talk because it's too much. But the thought is that you can poll that future in the loop. So like you can see there, like we're matching on the poll result of that future. And if we're ready, we're done. We can break out of the loop. In that case, I'm ignoring the return value, but because there is none. But yeah, you can break out of the loop. But if we're pending, you can see here we're parking the thread. And so you can see I grayed out this section, which I think is interesting to look at now. We're creating this waker here. So we're creating a context from a waker, and the waker is just a function that will capture a handle to the current thread and unpark it whenever we're ready to make forward progress. So the calls to thread park and current thread unpark are kind of related to each other. So we'll block at thread park, and then whenever the timer in this example will be ready to move forward, we're gonna unpark the thread and like continue execution from where we left it off. The crucial idea with this is that Rust lets us control the execution order of futures, in particular of tasks. And this is not to be taken for granted. I worked a lot with JavaScript and Node, and there you just don't know what's going to happen. Like, sure, you can monkey patch like the world, but you don't have access to how these futures are scheduled and run. So yeah, Rust is amazing for this, I think. Okay, so armed with this knowledge, let's go ahead and code a deterministic executor together. So I'm gonna switch gears and go here. Can everybody see okay? Yes? No? Cool. Okay, so here you can see we have a pretty simple program. We are instantiating an executor. We're going to implement this executor part in a moment. But the thought is that we're instantiating with Tokyo. And imagine we have this, this is a synthetic test. I'll show it in a second. But the thought is with this function is that it will return true when the test passes, and it will return false when it fails. And the reason why I say it's a synthetic test is that I wanted to showcase how these races can occur in real code. And so you can see here we're blocking on a future, and this future instantiates a lock to 0. It's just a counter. And then we have two sub-tasks, two sub-futures. One, we've got future 1 that will increment the counter only when it's 0. And then we have future 2 that will increment the counter only when it's 1. And we're use join again, like we saw before. And we're gonna deem this test as passing only when the value is 2. So in this case, clearly there's a problem. Like, this test will only pass when future 1 will finish before future 2. So I think this tells the story. So okay, let's go ahead and implement this Tokyo executor. So here you can see I have an enum that it's either a Tokyo executor or a test executor. And right now, like, the test executor has a runtime, which is just an empty struct. And here instead I have like a Tokyo runtime. So let's go ahead and create a Tokyo runtime. So I think the way you do this is like that. We unwrap because it might fail. And I'm putting it behind an arc because I want to be able to clone it around. I want this executor to be cloned around.
Do you want to specify current thread or multi-thread? I think
Sure. It doesn't really matter for this particular example, but yeah, I could. Yeah, so let's go ahead and, so yeah, here I have a test function that creates a test executor. So now I want to go ahead and implement spawn, and I want to match on self. So again, if it's test, we're not going to worry about it right now. And Tokyo already specifies a block on function, thankfully, which we can just call. Oh, sorry, this is spawn. Oops. I want to spawn, and we want to, here I'm going to put it in a box because the test executor will return a different kind of future, and I want to type erase that. And similar story with block on. So if I go here and I match, I want to use Tokyo's implementation of block on. Great, so now I can go ahead and run this test. So if I run it, you'll see it passed. Like, we know for sure that this has a problem, but it passed. And if I run it, like, it passes almost all the time. Now let's run it a bunch of times. And you can see here, like, an overwhelming majority of times, this thing is passing. Like, yes, it fails every now and then, but like, we don't know. And the worst is that we can't even be like, oh, okay, I saw a failing test. You can't reproduce it. You don't know why it failed. And so that's where this deterministic executor, a test executor, will come in handy. So let's start by creating this test executor. And an interesting thing about a test executor is that it's going to take a seed. And this goes back to what I talked to you about, the property testing behavior of, like, it's random, but it's seeded. So it's deterministic given the same seed. And so, yeah, in this case, what we could do is use the counter in this for loop to serve as a seed. So let's go ahead and pass it in. And yeah, the thought here is that we could create a runtime, which is this test runtime struct, and which right now is empty. So we'll need a couple of things here. We'll need an RNG, random number generator, which I'm using the ran crate for, which is pretty amazing crate. And then we want to track all the tasks that are running right now in the runtime. And I'm going to use a pretty simple vec of runnables. A runnable is an abstraction that the async task crate provides that is basically like a future that it's ready to be pulled. You'll see what I mean in a second. So yeah, let's go ahead and create this test runtime. So we'll say that we want to seed this from a U64, and then we'll start with an empty set of runnables. Okay, cool. So let's start with spawn. So I said I'm using the async task crate. So async task has a spawn method that lets you spawn a future and lets you provide a callback that is invoked anytime the future is ready to make progress. So this will be basically the call to wake that we saw before in the context. So anytime a certain stack of futures is ready to make progress, this callback is going to be invoked. And in this case, what we want to do is grab a clone of this runtime and move it into the callback and lock, unwrap, and push it up in there. Okay. And spawn returns a couple of a tuple. So it will return I think it returns a runnable first and then a task. That's right. So the runnable, what we want to do with this runnable is we don't want to run it right now because we're spawning. And so we're just going to like enqueue it for execution, which is just going to push into this vector. And then we want to return a task. We want to return a handle to this future that will resolve once the future is ready. So yeah, here we're going to async move, say, okay, task await. I'm basically trying to make the return type of async tasks similar to what Tokyo returns. Okay, great. I guess here I need to say runnables. Oops, great. Okay, and now we want to implement block on. So to implement block on, we want to do something similar to what we did before in that example in the slides. So we want to pin the future. I'm pinning it to the heap. I could pin it to the stack, but it doesn't matter for this. And so I'm going to instantiate a loop where I'm going to grab the future and pull it. And so now I need a context. So for right now, let's not worry about how we're going to create that context. Let's say that we're going to create a waker with this waker fn function that does nothing. And then we're going to create a context out of it. So context from waker. And I think this takes a reference, yeah. Great. So yeah, like we said, the future could either be ready, in which case, oops, I call this context, I should call it CX. So if the future is ready, we're gonna return its value. So we're fine. Now, what should happen if the future is pending? What I said before is that non-determinism is a nightmare. So ideally, what we want to do with this deterministic executor is make sure that anything that we could possibly await on is tracked by this executor. And so in this case, this is a pretty bare bones example where like all you can do in terms of async is just running futures. But the thought is that you could have a world where you mock the file system, you mock the network. You basically have this one-stop shop for all kinds of I/O and async progress where like you control everything that's happening. And so in this case, what we want to do is grab access to the runtime and take a look at, whether we have any runnables. And I want you to think about this, like if we know exactly everything that could happen in our system, if there is nothing else to run, if this future says that it's pending and there's nothing else to run, it means that this future cannot make progress. Like we can panic here. So yeah, future cannot make progress. Like this is basically eliminating the possibility of hanging tests, which is, I think, amazing. Okay, so what we want to do now is we want to grab one of these runnables, like the order of these runnables, like we see them in a certain order in the vector, but there's no, like we don't need to run them in the order in which they were pushed. So here we're going to pick a runnable at random and run it. This is what's going to give us the randomized execution order, similar to what property testing does. So let's grab the total set of runnables that can possibly run, and then pick one of them. I guess I'm going to do runtime, RNG, gen range, 0 to runnable count. And then I guess I want this to be immutable. Great, and then I'm going to pick the runnable. So runtime, runnables, swap remove, runnable AX, I call it runtime AX, runnable AX. Okay, now I can run the runnable, but before doing that, I'm gonna drop the lock I have to the runtime because this runnable, this future could enqueue more work, and so we don't wanna reentrantly lock as we're holding the lock, because that's gonna deadlock and never make progress. So, so we're dropping it, and now we can run the runnable. Great. So now if I run this, the first thing to notice is the amount of times that it fails are, we're picking from a random distribution. And so as we would expect, this is uniformly passing and failing. And so what's also interesting is that what I could do here is, as opposed to just running the test without knowing what's going on, I could print the seed And anytime I run, let's pick a seed at random, like 986 seed at random. Anytime I run seed 986, it's gonna fail all the time. It always fails. And so, yeah, I think this is pretty cool. Okay, so this is a pretty bare bones deterministic executor. I also wanted to show like a real world example of how this actually works in Zed. So in Zed we have, so it's a Rust application. We actually have both a server and an application. They're both written in Rust. And what we can do there is we're able to test the whole application end to end by simulating a network connection in the same process, where we randomize the execution order and like how often you receive packets, bytes, and we simulate the file system. Basically all these non-deterministic dependencies we can basically mock, which has a cost, but I argue that the cost the benefits outweigh the cost of maintaining those. They're pretty like standard and simple dependencies that don't change that much. So yeah, here you can see we have this GPUI test macro. GPUI is our UI framework, which we also use for running tests. Like the macro lives in that crate, could probably be extracted. But the idea is that, yeah, here we can create a server and we can create a bunch of clients that connect to that server. And yeah, the name of this test is test calling multiple users simultaneously. And the idea with it is similar to the idea I showcased in that example before, where like two clients were trying to join at the same time. Like this is similar. Like a client A is trying to call user B and user C at the same time, and this call to invite returns a task, which is it spawns inside. Yeah, we have other cool things like run until parked. Like we can basically let the whole system quiesce and like reach a moment of idleness. Like it could be idle, and we can assert about certain things about this particular harness. So yeah, I mean, here we're testing that the room participants are what we expect, B, C, and D, and they're pending. And again, here we can accept the call on all clients simultaneously, and again, make sure that this works. And the cool thing about this is that what we can do is we can, cargo test package. Let's see, this is the collab 2, and the name of the test is that. I can test it with no capture. So by default, this is exercising the whole application end to end, and I specified that I want 10 iterations by default. I could fix a seed. I could say that I only want to run seed 3, or start from seed 3. I can say that I want to run more than 10 iterations, and test everything I possibly could about this. Obviously, this is like we're picking from a uniform distribution, so like it's not going to be exhaustive, but we're going to have, with high probability, we're going to exercise a lot of the code paths in our application. Okay, we did it. I just want to, take a few moments to reflect on some key takeaways about this. So if there's anything you remember about this, is the following. Non-determinism is slowing you down. It could be due to understanding why your test is flaky on CI. It could be due to like a bug that you can never reproduce in production, because literally it happens 1% of the time. Like how do you go about understanding why that's failing? Even if you have great observability, it's still pretty tricky. Like we found this over and over again, which is why we invested in this infrastructure. Again, like this was pretty subtle. Like it's a pretty common mistake to invert these two expressions. It's a pretty easy mistake to make. Another key takeaway is that Rust unlocks fine-grained control over asynchrony. Again, it's not to be taken for granted. It's pretty amazing that you can do this in Rust. It's a pretty cool language and ecosystem. And I also want to invite you to think about this technique that you saw, to use it in your code base. Like what I like about this technique is that it's nothing fancy. Like we're using pretty standard components. We're not monkey patching. We're not doing anything fancy. We're it's what was it, like 100 lines of code? that you can use in your application today to fix async races and detect flaky tests. Thank you for listening.
Questions? Thank you very much for the talk. That was really, really interesting. Have you thought about or like looked at doing anything in condensing down the probability graphs so that you can sort of make some assertions about which code paths or which you are or aren't following?
We haven't, but it's a really good question. Like a few things we could do is like, you know, you could probably run a bunch of iterations and like understand, yeah, like flame graph, you know, a graph of which code paths are being taken more often, less often, to get a sense of, yeah, how much you're exercising your code. So that's a really good point. Another thing we could probably do, although it's going to be a little trickier, would be to simulate all possible execution orders. Like right now, what we're doing is picking at random, right? And so like you're just picking points in a pretty potentially big space. But yeah, I think it could be possible to understand exactly all possible combinations and permutations of a program's execution and, you know, test them all. Yeah.
Have you looked at Loom?
Yeah, that's what Loom does. Yeah, but Loom doesn't do it at the asynchronous level.
Exactly.
Like, yeah,
it's doing it like at the thread level, and
Right.
this is sort of taking one step up
Exactly.
into async and doing it async level, which
It's a really good question. Yeah, that's exactly what we could do, and they use some like state reduction technique to ensure it doesn't explode.
Yeah.
So yeah, I think something similar could be done here. This was pretty expedient in terms of like maintaining. You know, it's just 100 lines of code, pretty simple to code. We coded it together in 10 minutes. But yeah, it's a really good point.
No, thank you very much. It was really, really interesting.
Thank you very much for the presentation. Could you tell a bit more what exactly enables it in Rust, and what is the problem with doing that in other languages?
Yeah, so in many languages, you don't control the runtime. Like, for example, in JavaScript, you can define an asynchronous function and, you know, call it, but like you don't know what's running it. Like you don't control like who's, you know, making progress. Like V8 takes care of that in that world. And many other languages work like that. You don't have control over what it means to have these runnables or these tasks. Like, whereas in Rust, that's not part of the language. Like that's, you know, a library concern. In fact, Tokyo is a library. It's not part of Rust, and which is why we have multiple executors that work all differently and have different trade-offs.
So like this is basically about spawn and block on functions which you can arbitrarily call. Okay. Thank you.
Other questions?
So you mentioned one of the things that you could do was change the order of like you do network connections, and you would do some of that. And I think if I understood right, that's got to happen in that choice of where you picked a random function to a random future to run. You would have to pick a specific network thing to be active now, and that just sounds like it's getting really intimate knowledge of what the program is doing, and then someone writes some new code and something else happens.
So yeah, the premise with all of this is that you should have those dependencies like mocked out. So like if you're interacting with the file system, you should have like some you know, abstraction that like lets you talk to the file system so that you can swap it at, you know, test time to ensure determinism. In particular, like you don't necessarily need to though do it in that like in here. I guess let's go back to this. Yeah, so here I'm picking a random at random. Like one thing you could do is like typically those dependencies, like for example, a fake file system will return a future, right? It will be like async fn read, right? In the fake version of the file system, what you could do is you could grab a handle to this runtime and like simulate random awaits. Like you could basically be like, okay, I'm gonna await 5 times. You know, I'm gonna like yield back control to the executor 5 times. And that kind of like, so the thought with that is that like you don't need to know everything about your stubbed out, mucked out dependencies in the executor. You can, in each dependency, for example, if in the file system, you can, you know, await however many times you want in a random way, like you,
or even pull in that seed.
right? Yeah, exactly. That's what we do. That's what we do in Zed. Like we basically these fake dependencies have access to this RNG that like the test framework kind of plugs in, and you can use it to generate, you know, yield points and wait points. It's a really good question.
Thanks for the talk. It was awesome. So
you.
in the examples, you showed spawn and block on.
Mm-hmm.
But I believe in my mind, I do know how it interacts with join or join all, but can you maybe dive into this a little bit more?
So you mean join like, where was it? This, Tokyo join?
Yeah.
Yeah, this is like what it's doing under the hood is pretty straightforward. It's just like pulling both futures, like it pulls one future and then it pulls the other one. It's not doing anything fancy, like it's independent of how these tasks are executed. I don't know if we can look at how, I mean, this is gonna be mayhem, but at some point, yeah, here, like you're just pulling them like one after the other. That's all join does. It's nothing fancy and doesn't have to do with the executor at all. It's just about making sure you don't just pull one or the other. You like pull them for every like pull of the outer future, you pull them all at the same time.
Yeah, but you pull them deterministically, right? So
Yeah,
join
so,
pulls
yeah.
the first one first
Yeah,
and then
that's
the
right.
second. Can
So,
you
yeah.
also introduce some non-determinism in there as well?
Right, yeah, so if you use, I don't know how Tokyo works. I picked Tokyo because everybody knows it. Like in Zed, what we do is we use futures select biased, which will pull them in a certain deterministic order. One thing you could do is have a version of select that also uses the RNG to pull those futures at random and, you know, make sure that you join them as you would in production.
It can use an RNG for Tokyo as well.
Oh, it does that. Cool.
You could plug that in. It's under Tokyo stable.
Sweet. Okay.
You can plug that in. Oh.
Do you want to just repeat that?
Oh yeah, so he's saying that Tokyo actually lets you specify that. You can plug in an RNG at runtime, if I understand correctly, and this RNG could be seeded like the rest of the system that we saw.
Hi, I have a question. Of course, in an example like this, when you are just trying to mock a connection from a client, it's very easy to run 1,000 iterations and check what is the distribution of the failing cases. What happens when you have more complicated cases where you've got many more futures, or when you've got time dependencies where you can't afford to run, I don't know, 10,000 iterations to catch that one failure?
So the thought is that by mocking all those expensive dependencies, you can actually afford to run tens of thousands. In fact, like what we do, and for some of the most important piece of code that we need to make sure 100% or, you know, with a high probability works, is we run a lot of iterations, like 1 million iterations, like 10 million iterations. So yeah, that's the thought, like mocking those dependencies helps you afford more iterations. Of course, it's not perfect. Like I said, you know, with high probability, we're exercising all those code paths. But yeah, like to, I don't know what the person's name is, but to his point, what you could do is get a graph, or, you know, you could take a look, you could have some way of like understanding which code paths are being executed and like see, okay, are my distribution probabilities like allocated correctly? Like what can I do to make sure that I test all those code paths?
Thank you.
Mm-hmm.
Any other questions? No? Okay. So, thank you, Antonio.
Thank you.
Antonio Scandurra.